Hello everyone. What I'm gonna do in this short tutorial is discuss again in a little bit more detail the thermodynamics of aqueous solution, just to help some of you that have a little bit of a hard time understanding what's going on when you dissolve a compound, what changes when a compound is polar versus non-polar, and why non-polar compounds have a tendency to cluster instead of staying as a single molecule, dissolve as a single molecule in solution. So let me start by saying one thing, is that pure water itself, which is your starting point, that's what you always compare the thermodynamics of the energy of, is always, no matter whether you're dissolving a polar compound and a non-polar compound, is you're comparing to a solution of pure water, which is a solution where you have the maximum number of hydrogen bond possible for that specific amount of water. Okay. Water molecules not only have the maximum number of hydrogen bonds, but also have the maximum freedom to move around that solution. Okay, so because there is nothing really holding them tight or forcing them in a specific orientation where they can only be turned in a certain direction, because if they turn around, they cannot form bonds. They can form bonds with any molecules around them, so they have the freedom to move around and form as many molecules, as many hydrogen bonds as possible for, again, that amount of water molecules. So that's say, now, I hope you see that no matter what you add to that water, now you're adding something, whether it's polar, ionic, non-polar, it doesn't really matter. But you are adding something that will not have the same ability to form as many hydrogen bonds as if you had before pure water. Some of the compounds, like polar compounds, ionic compound, can replace some of these bonds, but they'll never, ever give the maximum total number of hydrogen bonds. You see, also, they'll constrain the molecules in their ability to move around, their freedom, and therefore, no matter what you add to an aqueous solution, you're going to have an effect in enthalpy. More specifically, you're going to increase the enthalpy. Do you remember? The lower the number of hydrogen bonds, the higher the enthalpy of any solution. Just remember, compare, for example, an aqueous solution, so a liquid water to a vapor water, right? There is much more energy in terms of kinetic energy in water molecules when they are in the gas form compared to the liquid form. They have higher enthalpy as a gas compared to a liquid form, so less bonds ultimately compared to when they are in a liquid form. So no matter what you add, enthalpy goes up, and some of the water molecules that were happily moving around when nothing was there, now they'll find themselves constrained around these other molecules, and therefore their entropy, their ability to move freely, to spread their energy, goes down. So no matter what you add, there is an impact ultimately on the delta G, which is the combination of these two factors together with the temperature in which this phenomenon, so adding this molecule to the solution, is taking place. So enthalpy will always go up, entropy will always decrease, no matter what you add, and the delta G, for this reason, will always increase. I want to stress one thing, that the delta G doesn't mean it becomes positive, but it might go from extremely negative value to a less of a negative value. And this because exactly of the temperature. Temperature adds kinetic energy and can keep this delta G negative. Okay, so that's why when you add salt, even though the delta G goes up, salt is going to be dissolved. It doesn't precipitate, it goes in the solution. It's a favorable process. Which leads to the next thing I'm going to discuss here, is that ultimately the ability to dissolve in an aqueous solution of any compound, it's a reflection of how much the compound impacts the enthalpy, the entropy, and therefore the delta G of that solution. You know, if a compound dissolves, as I was mentioning before, sodium chloride, you put it in water, it will dissolve. You know that the delta G of that process is still negative, okay, because of this relationship between the ability to dissolve, and the delta G. It's a favorable, spontaneous process. Putting salt in water, it's happening, the delta G is negative. Now, one thing I want to stress is that this is not written in stone. Okay, even with non-polar, extremely non-polar compounds, salt, if you keep adding more and more, because these molecules, that you are adding impact the enthalpy and the entropy, overall that impact may affect the delta G to a point where it brings it to be equal to 0 or higher than 0, making the process unfavorable, non-spontaneous, and causing precipitation of some of these molecules. Okay, so it's not written in stone that the delta G always be positive when you use polar non-polar molecules, even in that case. What is the difference between a polar non-polar compound is where this transition takes place. With non-polar molecules, this transition takes place very early at very low concentration. With polar molecules, ionic compounds, it takes place later, so you can add much more and dissolve it before the delta G transition to a positive volume, right? Keep in mind, again, just adding things to all of this, then we'll get into the details here, is that you can move this by playing with temperature. Again, so increase the temperature, and now you're moving this positive delta G more to the right. It can dissolve more solute, whether it's polar or non-polar. Okay, this can dissolve more than you could be at a lower temperature. So many factors can affect this. Okay. Now, let's start moving to the difference between polar and non-polar compounds, or I'll group together ionic and polar compounds versus non-polar or amphipathic, so molecules that have a polar head and a non-polar tail, like phospholipids, for example. I'll put them together all as non-polar compounds. Okay, just for clarity. Again, what I'm pointing to you earlier on is what is the effect, the difference between these two types of compounds when you compare it to pure water. Okay, which one has the largest impact compared to that solution of pure water, where all the water molecules were free and happy, forming all these bonds all the time, enjoying their time. All right, so let's look at one component at a time. Let's start with enthalpy. What is the difference between ionic and non-polar compounds, ionic and polar, and so on? So the ionic compounds like this one, or non-polar molecules that have a similar scenario, what happens there? You put sodium chloride, sodium and chloride, the ions that they separate, and they are surrounded by water molecule. This is referred to as solvation, okay, when the solvent molecules surround any molecule in there. So what happens there is that when this takes place, now, of course, ionic polar molecules, they reduce the number of hydrogen bonds that these water molecules could form, right? Because in some parts, particularly, you can imagine better when you're talking about polar molecules, imagine like an amino acid, a non-polar amino acid, which can still dissolve in water, right? It's still polar, but is less polar. Imagine the water molecules can form hydrogen bonds with the nitrogen, with the oxygen of the carboxy group, but then if they turn towards the non-polar component of that amino acid in the R group, they can't form that, right? So all these hydrogen bonds that this water molecule could form before, now they cannot be formed fully again, okay? So there is loss of hydrogen bonds. However, some of them can be replaced with interaction between the water molecules and the molecule that is dissolved. So in this case, sodium chloride or that polar amino acid. Sometimes some of the hydrogen bonds can be replaced. So the impact on the enthalpy, again, enthalpy is still going up, but is reduced by the ability of forming some more bonds here and there between water molecules and the molecule that dissolve, polar or ionic in this case. Now, this is different if you look at non-polar molecule. In this case is an amphipathic molecule, so it has a polar head and non-polar component. What we focus on is the non-polar tail right here. Now, these water molecules have less ability to form hydrogen bonds because something has been added to the solution to start with. And compared to polar non-ionic molecules, now these bonds, none of these bonds can be replaced when it comes to the polar tail. This molecule here can turn, when it turns around, cannot form hydrogen bonds with this hydrocarbon. All right, so there is loss of hydrogen bonds, and these bonds are not replaced by any hydrogen bonds with a non-polar component. Therefore, the impact on the enthalpy in this case is larger, right? Loss of hydrogen bonds, none of them replaced in that case. So you can see how polar and ionic compound, they have less of an impact on enthalpy. They still increase it, but less than non-polar and polar compounds. Now, what happens to entropy in the same scenario when we compare polar to non-polar compounds? What happens there is that for the same reason linked to the ability of forming these bonds, now these water molecules, they are surrounding, in this case, the ion, but in another case, the polar compound. So they can turn around, form some hydrogen bonds. Sometimes they cannot turn around, right? If they are in the non-polar component of the amino acid, they will be more constrained, because as soon as they turn around, they can form bonds. They will spend more time turn towards the side where there are other water molecules that can form hydrogen bonds with. So there is some reduction in the freedom of the movement of these water molecules, right? When they're solvating, when they're around the polar or the ionic compound. However, there is still some freedom in that case. So the ability to move is reduced with some compensation when this molecule turn around, forming the hydrogen bonds and so on. Again, because there is a reduction in the freedom of movement, entropy in this case is going down. Not dramatically, but it's going down. What happens when instead you're talking about a non-polar compound? Well, these molecules can't even turn around and form the hydrogen bonds. What it means is that they're basically constrained in a position where they try to maximize the number of bonds by being almost forced to stay always oriented towards other water molecules that can form the hydrogen bonds with, right? And therefore, these molecules are more constrained in this case compared to when it comes to a polar or ionic compound. Therefore, the impact on the entropy as well of non-polar molecules is much higher compared to the one of polar and non-polar molecules. So the change or the decrease in entropy with non-polar molecules is much higher than the one caused by polar or ionic compounds. Therefore, when we combine these things together, which is what the delta G is, right, together with temperature, assuming that the temperature, of course, is the same in both phenomena here. Now, when we combine these two things, so the change in enthalpy and in entropy, this is an S, and this is an S as well. I forgot to change it, my apologies. But you can see how the smaller change in entropy and the smaller increase in enthalpy here causes an increase of delta G with polar and ionic compound, which is less than what is caused by polar compounds, which increase the enthalpy much more dramatically and decrease the entropy. So this is an S again, much more dramatically than polar and non-polar and ionic compound. Now, I want to stress again one thing. The fact that the delta G goes up does not mean that this is not going to happen, because this delta G can still be negative because of the temperature here. If you lower the temperature, then of course this could go to a positive values in both scenarios. But this value right here of delta G can still be negative because of the temperature. Now, what it implies is that the solubility of polar and ionic compound is much higher, so it can take place at higher concentration than the one on non-polar compounds. But if you start with very little non-polar compound, they can still dissolve. Of course, when you increase the concentration, that's what I was saying here, a much smaller concentration, now the non-polar compound will move to a delta G, which is positive, and therefore will not dissolve anymore. Now, the last thing I want to discuss here is what happens to these non-polar compounds. As you know, now they do move from, they don't really stay dissolved as is usually, but they tend to cluster together. Why do they do that? And that's exactly based on what we discussed until now. The reason being that the impact ultimately in enthalpy and entropy is reduced when these nonpolar compounds cluster together. Why does this take place? It's ultimately because the surface, the total surface, if you think the amount of water that are constrained around the nonpolar compounds, right, is proportional to the total surface of these nonpolar compounds, right? And this total surface, it's less when these nonpolar compounds cluster together. Now, not only that, but also the number of hydrogen bonds that is lost is proportionate to the total surface. And therefore, so what's going to happen is that the overall effect in the enthalpy and in the entropy of nonpolar solution, now it's much less if the nonpolar molecules are combined together. When it comes to amphipathic molecules, now this is achieved even better when you find yourself with only the polar components being placed on the outside, the nonpolar component inside here, causing basically the formation of a very large polar complex, which now, again, goes back to similar to what happens with polar and ionic compounds, so with a smaller impact on the enthalpy and on the entropy of that. So, summarizing what I said in this very short tutorial, what's happening there? And again, please keep in mind this is an S here. I just forgot to change it from H to S when I did copy and paste. So, what did we discuss here? First of all, no matter what you put in a solution, this causes an increase in Gibbs free energy, right? And this because no matter what you add, there's going to be an increase in enthalpy. There is loss of hydrogen bonds compared to the pure solution of water. And some of the water molecules are constrained in a fixed position, more or less, depending on whether the compound is polar or non-polar, than when they were in pure water. Okay, so entropy goes down, enthalpy goes up, no matter what you dissolve in the aqueous solution. However, the impact, as we say before, of polar ionic molecules is smaller than the one of nonpolar molecules. The reason being, first of all, that some hydrogen bonds can be replaced in ionic with ionic and polar compounds, whereas it cannot be replaced when it comes to nonpolar compounds. Hence, the effect on the enthalpy is reduced. And for the same reason, ultimately, the water molecules here have a bit more freedom to move around when they're forming the solvation layer around the complexes here, compared to what happens when instead they're surrounded in a nonpolar molecule where they're basically forced to form hydrogen bonds only with the molecules opposite to the nonpolar compound. And therefore, there is a larger impact on the entropy with nonpolar compounds compared to polar compounds. Now, the last thing that we discuss is how this large impact ultimately is reduced by the reduction of the overall surface that this nonpolar compound, again, this one is amphipathic in this case, but these nonpolar compounds take place when they are clustered together. You have a reduction of the overall surface, which has an impact both in enthalpy and entropy, reducing the overall impact of these nonpolar compounds, and therefore the impact of the delta G. And that's why nonpolar compounds put in an aqueous solution have a tendency to cluster together. I hope everything is clear from this tutorial, and I'll be happy to take more questions when it comes to the class.